Hello, chemistry students. We're now ready to move on to our next chapter in chemistry. We're going to go back and look at a specific state of matter, and so we are going to be going over gases. And so we are going to spend this week talking about gases. We're going to start off by learning about different gas laws. And so each of these gas laws was discovered by another scientist, and so it is named therefore after them. And so our first topic, we're going to split into two parts. And so today we're going to look at the first of the three gas laws, and so we'll talk about that. And then tomorrow, then we'll look at the combined gas law, which takes those three gas laws and puts them together. And so over the next couple days, we're going to see the relationships between pressure, temperature, and volume on a constant amount of gas. And then we're going to also see how we can use the gas laws to solve problems involving the pressure, temperature, and volume of a constant amount of gas. There is going to be some math, as you would expect, in this chapter. However, it's nothing more than some basic algebra. And so we will go over how to do each of these problems. And so we're going to go ahead then and get started. Before we begin with the gas laws, I want to go back over briefly the kinetic molecular theory, or KMT, that we talked about in our previous chapter on the states of matter, because, again, we're dealing with the specific state of matter of gases. All right. Remember that the kinetic molecular theory says that gases are made up of tiny little particles that are separated by a large volume. We're going to have a couple assumptions in order to help simplify our study. We're going to first look to see, we're going to state that gas particles neither attract nor repel each other. And so we're going to go ahead and make that assumption. We're also going to assume that the gas particles are much smaller than the distances that are between them. So most of the gas is going to be empty space, much like an atom. All right, gas particles, as we talked about in the last chapter, are in a constant random motion. There is no kinetic energy lost when gas particles collide, and we'll also say that all gases have the same average kinetic energy of a given temperature. So we're going to use these assumptions to make our calculations a little bit easier. Let us start first by looking to see what happens when we compare the pressure and the volume of a gas. And so we're going to be looking at the work of Robert Boyle. And so Robert Boyle, he's also considered a father of chemistry. And so separate from the Lavoisiers, they're considered more the parents of modern chemistry, whereas Boyle was part of the transition of taking alchemy and making it into the science of chemistry. So in that respect, Boyle is considered the father of chemistry, although do remember that Antoine and Marie Lavoisier are considered the parents of modern chemistry because of the law of conservation of mass. All right. Anybody who's had a balloon, what happens to the pressure inside of the balloon when you squeeze it? So you're taking the balloon, you're going to be squeezing it together, and so you would expect that the pressure is going to go up. And so Boyle's law states that the volume of a given amount of gas held at a constant temperature varies inversely with the pressure. And so what that means then is if pressure goes up, the volume has to come down, or if the volume goes down, then the pressure has to come up. And so we're going to be using a simple mathematical relationship to show this. We have the pressure before, and the volume before, and the pressure and volume after. We're going to use 1 for before, 2 for after. And so what we can say, if we take the first pressure and multiply it by the first volume, that's going to equal the second pressure after times the second volume after as well. And so notice that we have to hold the amount of gas at a constant. And so we're going to see how pressure and volume change as we do this. All right. Let's take a look at an example. And so For anybody who's thrown a party or has been involved with a party, you can go to the store and purchase a helium tank to fill the balloons up with helium. If we have, for example, a sample of helium gas compressed in a tank, we're going to compress it from 4.0 liters to 2.5 liters at a constant temperature. If we're told that the pressure of the gas in the 4-liter volume is 210 kilopascals, we need to then determine what the new pressure is at 2.5 liters. And so even before we do any work, notice that we're starting at 4 liters and we're going down to 2.5 liters. And so as you remember, pressure is inversely related to volume, and therefore if the volume goes down, we would expect the pressure to go up. And so we're going to expect that our final solution is going to be greater than 210 kilopascals. And so we're going to go ahead and look to see how this is done. And so what we're going to do, we're going to plug in what we know. And so we're told that our initial pressure is 210 kilopascals, so this becomes our P1. We know that our initial volume was 4.0 liters, so that's our V1. This is going to equal our new pressure, which is P2, and then we're going to have our new volume, which is 2.5 liters. So notice we have 4 different variables, and you'll be given 3 of the variables, and you'll be asked to solve for the 4th one. And so what we're going to do, an easy way to do this, we're going to go ahead and we're going to take 210 times 4, and then we're going to divide that by the new pressure, or the new volume, I should say. I'm sorry. It should be 2.5. And so when I do that, I'm going to see that I end up getting something approximately 336 kilopascals. So notice that, in fact, the pressure did increase from 210 kilopascals to 336 kilopascals because the volume did, in fact, decrease. And so that is how you would do a type of Boyle's law problem. All right. Let's now turn our attention to look to compare the volume of a gas with its temperature. All right. Anybody who's ever played soccer or basketball or something with an inflatable ball knows that if you leave it outside in the wintertime, you find that it looks like it's low on air. And so what we can say then is there's a direct relationship between the temperature of a gas and the volume of the gas. And so if the temperature gets colder, the volume shrinks. If the temperature gets hotter, the volume of the gas will expand. And so basically, if you remember from last chapter, temperature is the measurement of the average kinetic energy of a sample of gas. If we increase the temperature, we're also increasing the amount of heat we're adding, and therefore the particles are going to be banging around the containers much more frequently, and therefore the volume is going to also have to then expand in order to accommodate for that. There is a gentleman by the name of Charles, and so he noticed this and came up with a law. His law basically says that the volume of a gas is directly proportional to its Kelvin temperature at a constant pressure. So notice that we're not using temperature in the Celsius scale, we're actually going to be using it in terms of Kelvin. And so the reason we have to use it in terms of Kelvin is because we have to base it upon the absolute scale. So notice Celsius is based upon both the freezing and the boiling of water. And so 0 degrees Celsius is where water melts or freezes. 100 degrees Celsius is where water boils or condenses. Absolute scale depends upon absolute zero. And so in order to first do these types of problems, in order to find Kelvin, we simply take the measurement in degrees Celsius and we add to that 273. So before you do these types of problems, you must remember to convert first between Celsius to Kelvin. And so the relationship here, Charles's law says that V1 over T1 equals V2 over T2. So the volume and temperature before equals the volume and temperature after, as long as we keep it at a constant pressure. And so Charles's law again compares the volume of a gas to its temperature. And we will see that they are, in fact, directly proportional. So as the volume goes up, the temperature goes up, or if the volume goes down, the temperature has to go down. All right, let's take a look at an example of this type of problem. We have a basketball on a summer day with a temperature of 75 degrees Celsius, has a volume of 2.58 liters. What will be its volume on a winter day with a temperature of 40 degrees Celsius, assuming the pressure remains constant? So remember what I said about volume and temperature. So if the temperature goes down, we know that the volume too must go down, which is why in the wintertime you see basketballs and other inflatable balls tend to look a little more depressed. And so the first thing we need to do is we have to convert both of our temperatures from Celsius to Kelvin. And so notice that we can take 75 degrees Celsius. If we add 273 to that, we'll end up getting 348 Kelvin. If we take 40 degrees Celsius and we add 273 to that, we end up getting 313 Kelvin. We plug those numbers into our Charles' law equation. We're interested in the new volume, which is our V2. And so in order to solve this problem, what we need to do is take 2.58, we divide by 348, and then we'll multiply by 313, and that should give us our new volume. And so let's go ahead and do that. And so I'm going to go ahead, I'm going to round this off to approximately 2.32 liters. And so the new volume here for the basketball is 2.32 liters, which makes sense because, again, we started off with a volume of 2.58 liters. It has shrunk down to 2.32 liters because it's wintertime and the temperature is colder, and thus the volume also has to go down as well. And so this is an example now of Charles' law. All right, we're going to do one more type of gas law today, and so we're going to now compare pressure to temperature. And so again, because we're dealing with temperature, we must always remember first to convert any of the Celsius temperatures to Kelvin, which is easy because all we have to do is take the Celsius reading and add 273 to that. And so that will then convert the two temperatures into Kelvin. Some of you might use a pressure cooker in your daily lives. And so a pressure cooker allows for the cooking of food at a much faster rate. By increasing the pressure inside of the cooker, you also therefore increase the temperature, and therefore the food that's inside gets cooked faster. And so pressure cooker does show a direct relationship between pressure and temperature. It also makes sense too because remember that the pressure of a gas is when we have the banging of the molecules against the sides of the container, and therefore if we add more heat, the particles are going to bang into the side of the container much quickly, and it's going to happen much more frequently, and therefore the pressure is going to go up. And so Gay-Lussac, who is a French scientist, also came up with a law to help describe this. And so what he said was that the pressure of a gas is directly proportional to its Kelvin temperature if the volume is held constant. And so notice that this law looks very similar to Charles' law, except instead of looking at volume and temperature, we're looking at pressure and temperature. So notice that we have P1 divided by T1 equals P2 divided by T2. And so again, we have to remember to first convert the temperatures to Kelvin, and then we can go ahead and plug in what we know and solve for our unknown. Here's an example of a Gay-Lussac problem. We have the pressure of a gas inside of a pressure cooker is 3.20 atmospheres at 22 degrees Celsius. If the temperature is raised to 60 degrees Celsius, what will be the gas pressure in the cooker? So notice again, we're given the temperature in terms of Celsius, so we know we first have to convert each of these to Kelvin. Remember, in order to do that, we simply take the Celsius reading and we add to that 273. And so 22 degrees Celsius, when we add 273 to that, will become 295 Kelvin. If we add 273 to 60 degrees Celsius, that's going to become 333 Kelvin. We're told that our initial pressure in the pressure cooker is 3.20 atmospheres, so we'll put that number here. Notice what we're looking for in this problem is our new pressure, so that's our P2. We plug in what we know, and so that we can solve for our new pressure. In order to solve this problem, we're going to take 3.20, divide by 295, and multiply by 333. So I'm going to go ahead and I will do that. And so again, what I'm going to do is I'm going to round this number up to 3.61. And so again, it doesn't matter how you round it, but the new pressure here is going to be 3.61 atmospheres. So notice that there was an increase from 3.20 atmospheres to 3.61 atmospheres. And so the homework then tonight, you'll be doing a total of 6 problems. 2 problems will be using Boyle's law, 2 problems will be using Charles's law, and 2 problems will be using Gay-Lussac's law. And so, again, go ahead and please make sure to do the homework, and I hope that you learned something from this. And so tomorrow then, we will then discuss the combined gas law. And so I hope you guys all have a great rest of the